Hi, welcome to part 2 of Regina Modern Math for 2025-26. This is going to be activities and games. I might have to break this up into 2 sections because, as you can see, there are a lot that I have brainstormed. But I'm going to start with the most directly mathematical of them, and a lot of these can be used to supplement the main learning goals, right, that I described in the previous video. Okay, so let's start with the fun stuff. Hailstone numbers. This is also called the Collatz sequence or the Collatz conjecture. The sort of rule for this little game is you start with a number, any number, and if it's odd, you multiply it by 3 and you add 1. If it's even, you divide it by 2. And you keep doing this to the result. So let's see what happens for a number like 5. 5 is odd, multiply it by 3 and you add 1, you get 16, divide by 2, 8, divide by 2, 4, divide by 2, 2, divide by 2, 1, multiply by 3 and add 1, you get 4. Alright, so this falls into a cycle, 4, 2, 1, 4, 2, 1, 4, 2, 1. Let's try something else, say 7. 7, 22, 11, 34, 17, oh boy, 17 times 3, 30, 51, 52, 52, even, 26, even, oops, 13, odd, 39, 40, 20, 10, 5. 16, 8, 4, 2, 1, 4, 2, 1, 4, 2, 1. No matter what number you pick, you will get this behavior. It goes down to 1. Now, the question is whether this happens for all numbers. I said no matter what number you pick. Yes, because we've checked every number up to quadrillions. Right? But there is no proof that this always happens. There's some proofs around it which are suggestive, like if there is a cycle that doesn't go to 421, it has some huge number of elements in that cycle, and it's bounded below by some huge number. But we don't have an actual proof. So this is a cool example of something that we think always works, but we don't know always works. As far as we can show, it always works, but we don't have a proof. Okay, cool. That's the hailstone numbers because it goes up and down, bounces, you know. Also called the Collatz, C-O-L-L-A-T-Z, sequence or Collatz function. Next, Fibonacci numbers. The rule for Fibonacci numbers is to get the next Fibonacci number, you add the previous 2. So if we start with, say, 0 and 1. 0, 1, all right, add these 2, you get 1. Add these 2, you get 2. Add these 2, you get 3. Add these 2, you get 5. Add these 2, you get 8, 13, and so on and so forth, however far you want to go. Or in symbols, the next Fibonacci number after the nth Fibonacci number is the nth Fibonacci number plus the n minus first Fibonacci number. Why is this interesting? Well, let's take a look at it in pictures. So we start 1, 1. So I'm going to draw a box size 1, a box of size 1 right next to it. Now, since there are 2 next to it, we add those up, we get a 2. And we can draw a box of size 2. But now we have 2 next to a 1. We can draw a box of size 3. Now we have a 3 next to a 2. We can draw a box of size 5 and size 8 and size 13. Now take a look at what happens if we draw quarter circles in all of these boxes. We get spiral. Same sort of spiral you find in snail shells, these shells in nature, Fibonacci numbers, also Fibonacci spirals also appear on pineapples, pine cones, the way leaves grow on trees. It's just found all over in nature, which is weird. And it's related to the golden ratio. It's related to a rectangle, which is kind of like what I've drawn. Very close. Maybe a little bit more on this side. Maybe a little bit less over here, but not much. Where if you take this length and you divide it by this length, you get the same numbers if you take this length and divide it by this length. That's a golden rectangle. And this spiral and the rectangles that you build approach the golden rectangles. So that's pretty cool as well. All right, interesting thing to introduce. Next thing. So that was called, I never spell this right. Google will correct you. So for all of these, I'm not giving like an exhaustive, lecture or activity, going through the entire activity. If something interests you, you want to present it, please look it up online and build something around that. If I had to do a full thing on all of these, it would take me to 20 hours. All right, Pascal's triangle. Okay, this is very interesting. It pops up in a lot of places, but the basic construction is simple. Start with a 1. Now for the next row, I just add 1s on both sides. Now for the third row, I add 1s on both sides. But here, I'm going to take the sum of the 2 numbers that are above it. And same here. And same here. And same here. There are several interesting things about this pattern. Let me continue with a few more lines. So, one thing you could do is take a look at the odd numbers. All right? Odd numbers, odd numbers, odd numbers, odd numbers. It actually makes, and this pattern will continue on. All of these numbers down here in this triangle here are going to be even. And then there's going to be this pattern repeated down here, and this pattern repeated down here. In fact, it turns into what's called the Sierpinski gasket. Another, which is a type of fractal, by the way. Oh, I forgot to put fractals on there, but fractals are another very cool thing that you can, put down an equation. Might not mean much to the kids, but then show them a video of like a zoom into the Mandelbrot set and say it all comes from this equation. Pretty cool. Another cool thing about Pascal's triangle is, well, here, let me ask you a question. How many ways are there to choose 2 objects from a set of 4 objects? What does that mean? So I've got 4 fingers. How many ways are there to choose 2 different fingers? Well, there's 1, 2, 3, 4, 5, 6. 0, 1, 2, 3, 4. Choose 0, 1, 2, 6. And that always works. So if you have like 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, 5, 6, 7 objects, and you want to choose 2 of them, there's 21 ways. 3 of them, there's 35 ways. 4 of them, there's 35 ways, because you're picking the you're picking the 3 of them that you're not picking, right? Same thing. Anyway, Pascal's triangle, Sierpinski gasket, as a side note, fractals. Cool stuff. And with a 45-minute period or something. You could even present something cool like that and then go on to drill with fractions or drill with multiplication, things like that. Let's see. Math in other bases. This is a great one to experience. I had a 6-year-old student at my mom's Montessori school that I taught to do addition and multiplication in basically any base. And in one day, she was brilliant, but she just had so much fun with it. When her parents came in at the end of the day, she was beside herself, happy to demonstrate to them this cool new thing she learned. So what does other bases mean? So normally we use base 10, all right? And so that means we have 10, it's a 4. 10 different symbols. But we didn't have to have exactly this many symbols. We could have fewer, we could have more. All right, let's see what happens if we have just 5 symbols. Could we still count? Could we still do math? Yes. Yes, we certainly could. After 0, 1, 2, 3, 4, we start reusing symbols. Just like we do normally, that's reusing symbols. That means one of the next number after this, right? One of these. So this next one will be one of these. And then one of these and one of these. All right, 11, 12, 13, 14, 20. Right? So I'm holding up 20 fingers. It's a cool thing to do, maybe count in base 3 or base 2. Base 3. There. Yeah. Base 3. 10, 11, 12, 20, 21, 22, 30, 31, and say, I'm holding up 31 fingers, and the others, but you can still do math with this. Like in base 3, you can have 201 plus 22. All right, well, 2 plus 1 is actually 10 in base 3. 2 plus 1 is 10, and 2 plus 1 is 10. So 201 plus 22 is 1,000 in base 3. Yeah, cool stuff. And it's very useful later on. Well, actually, this next thing is very useful later on about divisibility, etc. All right, so this is alternate bases. All right, cool thing to talk to them about. The next is very much related. Modular arithmetic. So you could say 7 divided by 3 is 2 with a remainder of 1. This remainder, an old word for it, is modulus. Right? So in modular arithmetic, we only keep track of the remainder. So, suppose you have a number, say let's work in mod 5 right now. Suppose you have a number that has a remainder 2 when you divide by 5, say 7. And you add to it something that has a remainder of 3 when you divide by 5, say 13. What you get is something that has a remainder of 0 when divided by 5. So another way you could write this is 2 plus 3 equals 0 up to remainder when divided by 5, mod 5. This is pretty cool, pretty powerful. I like to call it clock arithmetic. And I could go into some applications of this, but I got a lot to get through. So you can look up modular arithmetic, clock arithmetic. Okay, let's see, Platonic solids. Getting into geometry now. All right. One thing I like to do with the students is to bring in a cube, a tetrahedron, an octahedron, a dodecahedron, and an icosahedron. If you want to know where to find these, just look for a dice bag. There's going to be a 20-sided die, that's the icosahedron, 12-sided die, 8-sided die, 4-sided die, and a 6-sided die. Don't worry about the 10-sided dies. The 10-sided dies are not Platonic solids. What does Platonic solid mean? It means that all of the faces are the same shape and all of the vertices are interchangeable. Right? You can rotate any point on a 20-sided die to any other point and the shape would lay on top of itself perfectly. So now, how do we prove that these are the only Platonic solids? Well, let's start with the simplest type of face. Another thing about Platonic solids is that these are all regular polyhedra. So they're all polygons, regular polygons. All of the sides of the polygon that makes up a Platonic solid are the same size. So let's start with the smallest regular polygon, a triangle, right? All right, now, if we try to wrap it up into a square with just one more, it'll just lay flat. It won't be a solid figure. So let's get another one here. And so we know by geometry, 60 degrees, 60 degrees, 60 degrees, 180 degrees, this will make a straight line. All right, now when we fold it up, all right, we'll get sort of a pyramid type shape with a triangular base, which is also a regular triangle. So we can put 4 regular triangles together to make this shape. Tetrahedron, check. All right. Well, we can actually pack more of these triangles around here. We could do this, right? And rotate this up. So what would that look like? Well, now we have 4 triangles. 1, 2, 3, 4, with a square base. Well, take another copy of this, rotate it, put it on the bottom. Now, you have a polygon that is a regular polygon with 8 sides, octahedron. We can go even further. We can pack 5 around this thing and fold it up. We get the icosahedron. After taking 2 of these caps and rotating one and filling in the middle band with triangles. It takes a bit of imagination. But we can't go 6 because that'll just lay flat. All right, so we've exhausted triangles. Next, squares. Let's try 3 together. If we fold these together, we get the corner of a cube. Put 2 copies of these, rotate, mash them together, we get a cube. 4 squares will just lay flat. Dodecahedron. I'm sorry, I cannot draw pentagons to save my skin. Pentagons are just really hard to draw. Something like that. If we fold up these 3 and take another copy of it, put them together, fill in the middle with pentagons, we get a 12-sided dodecahedron. And we can't put another pentagon on there, and 3 hexagons would just lay flat. So that's it. That's all we can do. That's the proof. Platonic solids. Okay. Next. This is more like mental math exercises. One thing that I like to do with my little cousin David is a prime number. challenge, prime number contest. So, okay, first, what is a prime number? We talked about this last video. Prime number is a number that cannot be factored into integers other than 1 times itself. So like 6, 2 times 3, not a prime. 7, prime. Prime number challenge would be to maybe go around the room after you explain prime numbers and they think they've got it. And I say 2. Then the next person says 3. The next person says 5. The next person says 7. The next person needs to say 11, not 9, because 9 is composite. 13, not 15, 17. 19, oh, not 21, because that's 3 sevens. 23, not 25, that's 5 fives. 27 is 3 nines. 29, that's prime. Right? And you keep going, and you give them a little bit after each one for people to think, okay, is that composite, and try to call them on it. So that's prime number challenge. Okay. Another thing that my 10-year-old niece likes to do is mental doubling. We'll just start with some number. I mean, easiest number to start with is 1, and then double it. 2, double that. 4, double that. 8, double that. 16, 32, 64. Then it starts getting a little bit hard to do in your head. 128, 256, 512, 1024, 2048, 4, 0, 9, 6, 8, 1, 9, 2, 16, 3, 8, 4, 32, 7, 6, 8, and so on, as far as they can go. Mental doubling. Skip counting. So we all know skip counting. 2, 4, 8, 16, 3, 6, 9, 12, 5, 10, 15. What about skip counting not by whole numbers? What about skip counting by thirds? 1/3, 2/3, 1. 4/3, 5/3, 2. 7/3, 8/3, 3. It takes a little bit of thought to keep track. Okay, with those multiples of 3, then you go up by 1, and right, to simplify the fractions. But even tougher is when the fraction is not a prime number, right? And then try to simplify as much as you can every time you skip count. What do I mean by that? So 1/4, 1/2, 3/4, 1, 5/4, 3 halves, 7/4, 2, right? Maybe writing it on the board will be, well, especially if you're just starting out, right? Maybe write out 1/4, 2/4, 3/4, 4/4, 5/4, 6/4, 7/4, 8/4, right? And then say, oh, this is a half. This is 2 halves, but it's also 1. This is 3 halves. 1 half, 2 half, 3 half, 4 halves, which is the same as 2. Right? And so they get to see and try to jump down to the lowest thing, and to do this as a mental exercise. Very difficult, very entertaining. Okay, let's get counting with fractions. Let's go to something that is also very purely mathematical, but is sort of a different type of math. This is called graphs, and I'm not talking about x, y axis and graphing functions. This is graphs with dots and lines. First thing is just to explain what a graph is, right? A graph is some dots, and they're called nodes or points, connected by lines. So, and with a graph, the only thing that matters is how it's connected. So, this graph is the same as this graph, because it's connected the same way. Or you can think the two can be, wiggled around, one to lay on top of the other. But this would be a different graph than that. Okay? Or, for instance, 1, 2, 3, 4. You've got 4 dots, 3 lines, but here you've also got 4 dots and 3 lines, but you can't manipulate one without like breaking off a piece and sticking it onto another dot. You can't manipulate one to be the other. So these are different graphs. Okay, so that's graphs. Now, some interesting things to do with that. There's a problem called houses and utilities. Suppose we have 2 houses, house 1 and house 2, and you've got water, gas, and electric. Now, suppose all of these things have to go through exactly the same depth in the ground, so the pipes can't cross each other, they'll bump into each other. So you've got to connect up all the houses to all the utilities without any of the lines crossing. Well, first house is easy. Second house, you got that, and you got that, and you got that. Boom, you did it. All right. Now, try to do this with 1, 2, 3 houses and 1, 2, 3 utilities. All right? And these are good games to play with, like little pieces of flat stones or something and pieces of string, right? Try to do this. Well, first one, we just draw there. Second one, we can draw there. We can even draw that. Okay, fine. This house is connected, this utility is connected to all the houses. This house is connected to all the utilities. We need this house connected to this utility. Okay, we'll sneak around there. This utility, this house. Okay, now, all right, we need to connect this house to this utility. We can't do it. It's completely enclosed by this. Okay, so let's take this out and connect it this way. Okay. Let's see. Now we need to connect this house to this utility. Well, this utility is now completely enclosed. You can't do it. So this is an impossible problem. And the sort of jargon for this is that the, what is it called? It's called K3, but it's like a bipartite, complete bipartite graph or something like that. That this graph is not what's called planar. It can't be drawn without the lines crossing. So it's not planar. Okay, another problem with these dots and lines. Can you connect all of these dots to all of its neighbors, all the other dots, without crossing lines? Well, well, what about connecting these two? Yeah, you can do it. Well, what about 2, 3, 4, 5? Well, oh, we haven't connected these two. And this one's completely enclosed. In fact, again, this is impossible. This is not planar. The only way you can connect these 5 dots with lines is to have crossing lines. Like that. Or something like that. Okay. Another thing we can ask about these graphs is, are there cycles? Like things that, that you can go from one dot back to itself without reusing lines. If you don't have a cycle, you get what's called a tree. So that would be a tree. That would be a tree. In fact, these are the only 2 trees that have 1, 2, 3, 4 dots. An interesting question is to ask how many trees have 5 dots? How many trees have 6 dots? It gets really cool. It's about around 7 dots is where it gets very interesting. Counting trees. And here's a classic problem. It's got a story with it too. So in the village of Königsberg was built around a river. So here's a river. All right. Now, in the river, there were 2 large islands. All right. And the city was built on both sides of the river and on both these islands. Right. Covered all of them. There were 2 bridges from this larger island to the top bank, 2 bridges from the larger island to the south bank, a bridge between the islands, and a bridge from island to the north bank, island to the south bank. So the 7 bridges of Königsberg. The bet, there was an old bet that people used to make with each other, that whether you can cross all of the 7 bridges of Königsberg only once, right, on a tour of Königsberg. Cross all of the 7 bridges only once. It turns out to be impossible. So a way to motivate this might be to say, okay, let's use this stone to be the north bank, this stone to be the big island, this stone to be the small island, this stone to be the south bank, and we'll use strings as bridges. All right, now start at any place you like, pick up a string, take it away, then start at the place that the string ends, pick up another string, and see if you can pick up all the string. Right? The reason this doesn't work is that all of these things are odd. Right? And if you have an odd vertex and you start there, well, you have to leave it, you've got to go back to it, and then you've got to leave it again. So it could be the start place, but it can't also be the end place. It's got to be, hold on. That's a little bit more complicated to show. What's easier to show is that you can't do a tour like this and end up in the same location that you started. So, suppose this is, here it is. Suppose this dot with 3 bridges is in the middle of your trip, right? Well, you have to cross all 3 bridges. The first bridge you cross takes you, say, onto the north bank. The second bridge you cross takes you off the north bank. But then you need to cross that 3rd bridge to the north bank, and if it's your 3rd bridge that you're crossing, you've got to go onto the north bank. So it can't be a middle spot in your tour. It has to be the end. Or it has to be the beginning. Go out, go in, go out. Right? So a dot with an odd number of edges leading off of it has to be either the beginning or end of a tour like this. And since there's 1, 2, 3, 4 dots that have an odd number of edges sticking out of it, they can't all be the beginning and end, so it's impossible. Interesting. And last time I showed this to Bethlehem, they were drawing up all sorts of things on the board, all these graphs on the board. Can you walk this one? Can you walk this one? You know, and that was fun. Oh, the sun went out. Hold on, let me turn on the light. All right. Okay, so that's enough of the graphs. On to some more like games, activities, games, things like that. Checkers. One thing I wanted to point out about checkers is that there's a rule in the game that is often ignored, but shouldn't be, because at high level play it becomes very important to set up a win condition. In checkers, if you can capture one of your opponent's pieces, you have to. Right? If you've got multiple ways to capture, you can choose, but if you can capture, you have to capture. That's all I want to say about checkers. Chess, you all know chess. Shogi. It is a Japanese form of chess with less like ranged pieces, less powerful pieces, but which makes the game a little bit slower. But the real kicker here of shogi is that when you capture an opponent's piece on your turn, you can put that piece down on the board under your control, under some conditions. Very slight, but you put it anywhere under your control. That makes the game very, very interesting. One of Matthew's favorite, by the way. Go. So, Emmanuel Lasker, I think it was, who was a chess grand champion, said once that while the rules of chess are so Byzantine and complex that they could only have been created by humans, the rules of Go are such utter elegance and simplicity that if there are aliens on other planets, they play Go. It was considered one of the toughest challenges for artificial intelligence. It was beaten just a few years ago by AlphaGo. Google's AlphaGo beat the strongest Go player in the world. Go is played on a board without... Stop it! Stop it!
In a 2016 match.
2016. Okay, stop. I didn't ask you. I was referring to you, I didn't ask you. Stupid. Okay. So this is a Go board. Players place black and white stones on the intersections. Only a couple of rules. The spots next to a stone, stones of the same color connected by lines are part of the same group. The empty spots around a group connected by lines are its liberties. As soon as the last liberty is filled with a stone of a different color, the group is captured. The idea is to surround and control pieces of the board. Very much strategic, very pattern matching type game, and very much a game of balance. You've got to spread out enough to get more territory than your opponent, but not so much that you can be invaded. This is a fascinating game. For beginners, I would say maybe make a little 9x9 or 7x7 board, right? And they can learn the rules playing that and have some fun. Even professionals love playing on a 9x9 board. The standard board is 19x19. All right, that's chess, shogi, Go, checkers, all those good activities, good games. Another game is Nim. All right. Now in Nim, one player takes a bunch of stones and puts them into some number of piles. Say I have 3 in this pile, I've got 2 in this pile, and I've got 4 in this pile. All right. Then the other player gets some minutes to look at the board, and then the other player chooses whether to go first or second. All right. And then on the player's turns, they take 1 or more stones from any one of the piles. So for instance, if it's my turn, I could take these 3 stones from this pile. But then on the other player's turn, they can't take 1 stone from this and 4 from this, or 1 stone from this and 1 from this. They have to take from a single pile. So suppose they do this. And then I can do this, and then they can do this, and then I lose because I take the last stone. The loser is the person who is forced to take the last stone. And that's Nim. Another simple game, dots and boxes. Maybe you played as a child. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It could be played on any size grid, but players take turns putting lines. So I'll put a line here, then somebody else puts a line here, then I'll put a line here, somebody else puts a line there, somebody screws up and puts a line there. Well then, I get to put a line here, put my initial in there, and put a line somewhere else. Take another turn. Well, and they put a line here, and I put a line here, and they put a line here. and then I put a line here, put a line here, and put a line, well, they get the rest of it. So they put a line here, they put a line, well, it doesn't matter, because then I win. Right? Dots and boxes. Some puzzles. I think it's pretty well known that I love Sudoku, but there is a type of Sudoku called variant Sudoku. Which requires a lot more varied logic than normal Sudoku. There's things like thermometers, where the numbers have to increase along with thermometer, or German whisper lines, where the numbers have to differ by at least 5 going along the line, or all sorts of different crazy rules that lead to some very fascinating puzzles. So variant Sudoku, a channel that has a bunch of these variant Sudokus, a YouTube channel, is Cracking the Cryptic. Cracking the Cryptic. Another puzzle genre is Picross or Picross. What it does is has a grid. Let's say it's 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, something like that. And then there'll be like a picture drawn on here. There we are, 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 there we are. It's a little house, all right? There'll be numbers, 1, 3, 1, 1, 1, 3, 1, 1, 1, 1, and then 0, 1, 1, 1, 1, 1, 1, 3, 1, 1, 1, 1, 1. And then you won't see the house. You just get an empty grid. And you've got to figure out from these numbers what the picture is. Right? So easy to start here, because 1 space, 1, 2, 3 space 1, all of these groups have to have a space in between them. So this has to be that, 1, 2, 3, that, okay. Well, all of these groups are 1, so you know that's not in the picture, that's not in the picture, and so on. That sort of reasoning. P-cross. Like a picture crossword. Okay, got through all of it. One source of material that I have, especially for high school, junior high, are YouTube videos. You know, I watch math YouTube videos, and I'll just straight up steal from them. Some good channels are 3 Blue, BLUE, 1 Brown, Number File. An older one, she's not making videos anymore, but she's really good, is By Heart, Mathologer. Let's see, what else? I know I'm forgetting some. Wrath of Math. Veritasium. Has a lot of good content, math, science, all sorts of stuff. But yeah, I would urge you to subscribe to these so it comes up on your feed if you do any browsing of YouTube, and see if there's anything that interests you that comes up. And yeah, I think it's a great source of material for teaching. Okay, thank you very much. If there's any questions, please let me know, and I'd be happy to explain any of these in more depth. Thanks.